looks like I'm moving. You want to step out and make sure you can hear me? Or is that you? This is us, Dinesh. Okay. Good morning, everyone. Welcome to our annual summer lecture series in biostatistics for clinical and translational researchers. My name is Jo Wick, and I am a faculty in the Department of Biostatistics at the University of Kansas Medical Center, and I will be with you for the next 4 Fridays. Just a couple of reminders. If you traveled here from somewhere else and need your parking validated, you can come and see me right after, and I'll give you a sticker for your ticket. That way you don't have to pay for parking. I will also be sharing with everyone the recorded podcasts once these are processed with a reason Panopto to do screen capture and audio capture for the next 4 weeks. So if you're ever not able to join us live in person or live online, you'll be able to pick up on anything that you missed by a recording. And so those will be sent out by email. Everyone should have access to view the link, view the recording, probably right after the session ends. My office location is actually just upstairs in Robinson. That's where all the faculty offices are for biostatistics. We are a highly collaborative department, so if you ever have any biostatistical needs, we have a project registration link on our department website where you can just go in, put in some simple information, you can get some free kind of in-kind service for your projects, or if you wanted to formally collaborate on grants or things like that, we also have those services as well. In addition to project collaboration, grant, protocol development, we also have a student tutoring lab. Our PhD students are housed in the ground floor of Robinson, and they're there every Friday during semesters from 9 to 3, closed at noon, to help students and residents and fellows with any of their research project needs, as well as maybe any statistics homework issues that you may have if you're taking stats classes. So the purpose of this class is just to give everyone, for those of you who are familiar with biostatistics from your training, a refresher on some principles of how we conduct research in the health sciences, understanding the role statistics plays in what you do every day in terms of defining a research question and figuring out how to address that with some kind of study, balancing the true rigor of experimentation with feasibility, whether it be for ethical reasons or for resource reasons, seeing how we are a true core component of evidence-based medicine. So that's what we're going to focus on today, is just kind of defining what statistics is, what it does, how it facilitates making evidence-based decisions. Then we're going to go into study design. Next week, we'll get right into how data is analyzed based on a particular type of research question and a study design. And we'll talk about the pros and cons. We'll do that using real articles from the medical literature. But the key will be having you giving you some experience or some foundation from which you can start to critically assess your own literature, or maybe think about how you would address different questions that you have in your own research. So today, again, it will be kind of an introductory session. We'll talk about statistics, the role that it plays in quantifying variability and quantifying uncertainty in decisions and estimates. And then we'll get into hypothesis testing, which is kind of the meat. In past years, we have covered a lot of foundational material in terms of types of data, levels of measurement. I also have that information podcast for people who might have less of a stats background, who might want to go and take a look at that. It's probably something that you're familiar with, but it's always a good refresher to see some foundational material from which you can build upon for this more complex information. Before we get into the statistics part of the class, I want to offer you some information or some updates on our research IT infrastructure here at KU Med and some of the things that the department offers to clinical and translational researchers for their either their data management needs, their project management needs, and other things related to either observational studies or clinical trials. And I'm going to welcome our Director of Research IT, Dinesh. I will let him pronounce his last name. I've worked with him for many years and I still can't do it. I don't want to mess it up. And
Thank you.
I'll let you switch over.
Thank you, Dr. Vic. Good morning, everybody. Myself, Dinesh Pal Mudarantakam. I work within Department of Biostatistics as Director of Research Information Technology. We have grown from just a clinical trial management system to a level where today we have the entire ecosystem. I'm going to jump to this slide to just show the leverage of various systems that our team manages as of today. So we have C3OD, which we call as the Cancer Curated Clinical Outcomes Database, which is more or less like a data warehouse where we pull data from multiple sources, like the EMR, the tumor registry, the biospecimen, and the plan is to bring in omics and some of the sequencing data too. And the volunteers is nothing but a patient screening system where if someone would like to recruit patients for their upcoming clinical trial, that would act as their screening system, like a patient log. And e-research or the CRIS system.
You can check the
Sure.
Okay.
Most of you all are familiar with e-research or the CRIS system, which is the clinical trial management system, and the pharmacy, the investigational drug pharmacy, started using the IDS system because everybody is being treated on a drug, and the IDS, the investigational pharmacy, dispenses a drug for research purposes, then they use the IDS system. So before getting into the weeds, let me give some background and talk about some of the stuff that we do. We are heavily involved with the Cancer Center in conducting research. My background is I have a master's in computer science and a master's in business administration. What we do is within the Department of Biostatistics, with all the collaboration with cancer and non-cancer studies, we help facilitate research from phase 1 to phase 3 clinical trials. So just to give some insight of what phase 1 is, most of you all might be familiar. These are the same slides I used for our other class, so I'm just trying to go through this just so it would be like a refresher. So a phase 1 is a small study with a sample size anywhere between 20 to 100, and this is done for drugs that are being used or experimented with the patients for the first time. So before this, if there was a drug that pharma has discovered or has come up with a new dosage, then they probably have implemented on the mice or mouse, on those kind of stuff. So this phase 1, when they come to us, then they try to do it with a sample size of 20 to 100 among the healthy participants to find out what would be the optimal dosage. So that's where dose escalation kind of study is what we do. So how it is a teamwork is because our statisticians on the other side are designing the study and trying to figure out what is the optimal sample size, at the same time what kind of method should be used, and also understanding the population on the hand that we have at KU. instead of just coming up with, oh, 100 would be a good sample size for the study, but if we cannot recruit 100, then it is not worth projecting 100. So that's where we work hand in hand with our statistician to determine whether for this phase one, can we do a study of using this sample size or not. So after we do a phase one, if phase one is successful, then we move on to a phase two, which is usually a randomized trial, and the randomization could be either blinded or unblinded. In order to avoid bias, what we usually suggest is to do a blinded study. But again, when we are doing randomized trial, there are multiple ways to randomize your population. Either we could randomize them using 2-arm, 3-arm, and then also different kinds of randomization like clustered randomization or Bayesian adaptive randomization. So depending upon the aim, depending upon the goal, and also the timeline, our statistician understand what method or what kind of randomization would work best. And if phase two is successful, then the drug or the new treatment moves on to the phase three. So phase three is larger. So going back to phase two is larger than phase one, definitely. So now phase three is larger than phase two, but the 70 to 90% of studies that enter into phase three are able to successfully complete phase three. So phase three is usually the phase at phase three. What the pharma or FDA is trying to find out is what are the list of side effects that this drug could cause, and so just compiling that entire list and having to see that is what they're trying to do. I don't know, when you're driving, on your radio or on your TV, you see a lot of advertisement, right? Oh, by the way, please ask your doctor or physician if this would work best for you, because then at the end, then they suggest these are some of the side effects. So how they came to know that the side effects are caused by using that treatment is because at some point they have done a phase three trial to understand what could be the side effects. So the phase four usually is not done here. Phase four are usually conducted by pharmas at the FCRO, and the phase four is usually done to determine whether if the drug is cost effective, whether it is providing the effect, and is it fruitful, is what they're trying to determine. And by the time they are conducting phase four, sometimes the drug is already available in the market, but it's just prescribed by the physicians. It's not available for the counter. So, so if in order to do all this, in order to conduct any of these phase four, with keeping in mind all these different trials that we do, so we also partner with NIH, we directly partner with NCI. We have pharma partners who come to us and ask us what's the feasibility using their plan. And then apart from all those, we have our principal investigators who come to us and try to find the feasibility. So I'm not going to talk more about e-research here, which is our CTMS system, which is our clinical trial management system. I'm going to talk about our C3OD, and then also show some other niche tool that is available for accrual prediction. So, by the way, any questions, comments with regards to this platform or any of the platforms that we support, just feel free to email me. Just a quick slide here about recruitment. So recruitment is very expensive, by the way. Most of the times recruitment is ignored on some of the clinical trials. So you can see we have done some literature review where we found out that an average cost to recruit a patient is $270 or equivalent to 7.1 hours of a clinician. So it's time consuming, it's expensive, and this is for just phase one, phase two trial. So when we look at the phase one, phase two trial, we just thought we'll take an example of a study, and you can see that number of evaluations. So we had to evaluate 490 patients to just enroll 39 participants. Because every clinical trial, there is a set of inclusion and exclusion criteria. So unless a participant or a patient is qualified and gets through all those inclusion exclusion criteria, then only we can enroll a participant. If not, then if we enroll a patient and we know that they're not qualified, then that would be a protocol deviation or a violation. So here, if we see, in order to get someone who fits that criteria, we had to go through 490 participants for this phase one trial, and then we were able to recruit only 39 out of those 490. So approximately around 451 are all screen failures. So the amount that we are spending is too high. In order to avoid all this kind of stuff, what we have done over the years is we are pulling the data from EHR, and we are looking at various common variables across these data sources. And once we have pulled in, we wanted to do a validation. So we took these recently concluded investigator-initiated trials that were conducted at our cancer center, and out of those, we could see that these trials that we took those inclusion exclusion criteria and we ran it through our C3OD, and we were able to discover every patient that were already recruited onto the trial, except for this one study where you see only 81% has matched, which means we had a couple of patients who were not discovered by using the C3OD, and the reason was those patients where their inclusion exclusion criteria were overwritten by the PI. Those were very simple inclusion exclusion criteria, such as like the tumor size being, if the inclusion criteria said the tumor size has to be like 2 centimeters or something, even though their tumor size was little more than 2 centimeters, the PI has let the patient be enrolled onto the study. So this is how the C3OD works. It's a reverse funnel structure. So it's actually a funnel structure, a reverse pyramid structure. So we keep adding each and every inclusion and exclusion criteria until we attain the overall patient population size. So in general, if we didn't have the C3OD, like how we have seen a few slides earlier, our nurse or our physician would have gone and had to screen the entire 2,707 patients to identify just these 87 patients. So what we are trying to do is we are trying to save them time, and we are giving them a list of just 87 participants instead of 2,707 patients. So this is a quick video of how this works. So this is against the dummy data. So users could go in and plug in age range from 20 to 40, and it will give a count. And then they can go back and plug in a BMI with range 15 to 25. And this should narrow down the count. So we can see that here as a funnel structure, we have been adding the inclusion criteria. So now I'm going to use an exclusion criteria where I'm removing patients who have a smoking status. So that's how you can narrow your patient population size. And now let's move on to, the other important thing is It's all good. We planned for the study. We have a list of participants. Now, as a PI, as a study team, I start recruiting. But at times, what happens is during the study process, usually we ignore how we are making progress. Are we recruiting? Are we keeping a tab on our recruitment? Do we have enough patients so that my statistician can run his analysis or her analysis and give me a report at the end of the study? So in order to uh, make make sure, in order to monitor our accrual, our statisticians, what they have done is they have developed accrual app which works on a Bayesian adaptive design. So we took this algorithm and we implemented this on top of our data from all our cancer center trials. So how this looks is this is how it looks. So the URL to get to the app is accrual.kumc.edu. So it works only when you're on the campus because it's on the intranet. And what it does is it allows users or the physicians or the clinical trial folks to monitor their study, how well their study is doing. Let's look at this first study here. So this study has target sample size is 12, and the expected duration is 24 months, and it has started in October 17, 2017. So the 24 months from October 2017 will be 2019 October. But depending upon its current rate, which is it has accrued only 0 participants, it is saying that the accrual could end, or the study can accrue 12 patients by July 2020. So that's the kind of projection that we are trying to get. So some of the graphs based upon, so when we click on this, the hyperlink here, the graph shows the gray area is the red line is actual 24 months, and this white line is the current accrual rate. So always the PI and the study team have to make sure that this white line stays before this red line in order to complete their study on time. So any questions?
This software, the CPOB, applies to other specialty or just like cancer patients only?
Make sure you repeat the question.
Sure. The question is does CPOD only apply to cancer? Our current IRB to develop this data warehouse currently pertains to cancer and preventive cancer, but we look forward to partner with other people outside of that too. Any other questions? Okay, thank you. I'll turn it back to Dr. Vic here.
Thank you, Dinesh. Okay, we're going to cover 2 topics today. As slow or as fast as you all want. I encourage everyone to answer questions if you have them, especially as it relates to your own work, or if you need any clarification on any words that I'm using or concepts. So we'll have plenty of time to cover an introduction to statistics, just what it is and what we do with it, why we use it, and then we'll move forward into the most common types of study designs, which ones are really truly experiments, and which ones are less rigorous than that. And we'll talk about the pros and cons of each. And then next week we will get to actually taking a look at how research questions were addressed in the context of those types of study designs. And then we'll look at the specific statistical methods that were used to both describe the data and to draw inferences from it. So the formal definition of the science of statistics is it's the science of decision making in the presence of uncertainty. So when we're dealing with samples rather than populations, there's always some ambiguity in our conclusions because we don't have 100% of the information that's available if we were to have a census, if you will, of all of the information in a particular patient population. Some of the kinds of questions that we address using statistics, we might want to predict something like a patient's long-term chances of successfully quitting smoking when therapy includes both nicotine replacement and varenicline. So what will a patient's outcome look like in the future based on what we know up to a certain point? We might also be interested in estimating things, something as simple as the prevalence of obesity in our country, which is not really all that straightforward, actually. We have to do a lot of adjusting if we're using samples to make sure that the sample is truly reflective of the population. And then we might also want to do inferences where we compare groups. For instance, we might have two different interventions for coronary heart disease, one being surgical and one being medicine-based. We might want to see which of these is better, or are there any differences? So formal comparisons of outcomes for patients who underwent different types of treatments for the same thing. So as I alluded to, statistics, the science, actually can be broken down into three different subfields. The one that we're going to talk about today is the one right in the middle, which is how we design studies. Not all studies are true experiments. We'll see that in a moment. But experimental design is a set of techniques for planning and conducting experiments. And I think, unfortunately, whenever you take a statistics class, just a regular statistics class, either an undergraduate or maybe an early graduate school, we don't emphasize this aspect enough. We don't understand, unless we're basic scientists who actually perform laboratory experiments, we don't quite understand the rigor necessary in order to get a valid estimate of a relationship. So what we'll look at are techniques for minimizing bias and techniques for minimizing error or noise, so we can get a precise, valid estimate of an association or a difference, or to get a good picture of a true effect in a population. What we're most familiar with covering in stats classes are the other two, descriptive statistics and inferential statistics. Descriptive statistics are just the techniques and tools we use to process data, to summarize it using numerical measures like the mean or the median or the standard deviation, or graphics for presenting and describing that data. Inferential statistics, that's the tests. We're trying to draw conclusions about something, some kind of phenomenon, based on sample data by applying statistical methods to that data. And so what we're doing in inference is we're just trying to figure out what's real information and what's just noise. And that's all generated preferably by experimentation, but it can also be done through observation as well. We just have to understand that the context really defines the limitations of the results of any kind of inferential statistical method. So again, the way statistics is used is it allows us to figure out where the variability in outcomes is coming from. So what we usually do when we set up an experiment is we try to control different sources of influence on a patient's outcome, either by limiting the type of patients that we approach for our study, or standardizing processes and procedures, standardizing the way treatment is administered, standardizing the way we observe them and collect that information from them in order to figure out and minimize not only the different types of variability that can impact an outcome, but also to be able to allocate the observed variability in an outcome to those different sources. So here's just a little picture again. This is important because everything that we do depends on samples. We don't ever know the truth. All we know is what the data tells us, and the data, again, could be very flawed, or it could be a quite accurate representation of reality. Here's an example of how statistics can play a role in both designing an experiment and also in, again, allocating variability in an outcome to different potential sources in a true study. So this is a contrived example, obviously, but it's very simple so we can focus on the concept. Suppose that a researcher is interested in evaluating whether drinking coffee increases the risk of lung cancer. So here's another great take-home point. Even though we know that true experimentation is the gold standard for identifying an association, it's not always possible. Usually, it could be because it's unethical or not feasible to do some aspect of a true experiment. So in this case, randomizing people to the exposure really isn't feasible. We don't randomize individuals to drink coffee or to drink a little bit or a lot of coffee. People just self-select into doing that. So this is an observational study by nature because true experimentation just isn't really feasible in this case. I'm using some terminology here that I haven't gotten quite to defining. A true experimental study, one aspect of that means that the investigator, the researcher, is actually controlling the exposure assignment. So if a subject agrees to participate, the researcher assigns the exposure, preferably through some kind of random mechanism, but not always. An observational study means that the participants have self-selected. You're just observing what's happening naturally. The problem with observational study is that there's a lot of potential confounding that can happen. So for instance, if I like to drink coffee, what else might I like to do? So those are the kinds of things that we have to think of in terms of what other potential sources of influence on my risk of lung cancer could be also associated with my choice to drink coffee. And that's the problem with observation. Just plain old observation has these risks of bias. So what we do instead of randomizing in this case is we work within the limitations of the study and we just observe whether people are exposed to coffee or unexposed. And we also, another aspect of this is we trust that they tell us that they're exposed or unexposed, right? Sometimes in studies, there may be sensitive questions where you actually might get what's called misclassification of exposure. So if you ask people if they're on birth control or if they're having unprotected sex, that's a very sensitive topic about their drinking behavior in terms of alcohol or their drug use. So again, you can see other potential problems when we're trying to get precise information about the result of exposure. So this very simple study, we'll see in a moment, is actually a cohort study where we look to see whether individuals are exposed or unexposed to the, in this case, coffee drinking. And we're trusting that they're telling us the truth about their exposure. But then we look forward in time, we follow them forward and determine how many of the individuals in each of these two groups, each of these two cohorts, actually end up with a lung cancer diagnosis. Again, another aspect of the studies that we have to think about is just the feasibility of this in general. If we are identifying people who are drinking coffee now, how long will we have to follow them in the future before we get enough people who are diagnosed with lung cancer? This might not be feasible prospectively anyway, right? So again, another aspect of balancing the principles of experimental design with just feasibility. But let's suppose that this is feasible for a moment. We follow them forward in time. Maybe these are 45 to 80-year-old men, and we're following them forward in time to determine their lung cancer diagnosis. And so ignore the notation here. I'm just showing you that there's a couple of rates. These are basically proportions, percents, if you will, in the two groups. Also suppose that when we calculate the rate of lung cancer in each of these groups, we find that the rate of lung cancer diagnosis is actually higher in people who drink coffee. So what's the problem with this study? Can we just right off the bat write up our paper, oh, this was really exciting, we found higher incidence of lung cancer diagnosis in coffee drinkers? What does that mean? We probably shouldn't, right? We have to think about all the aspects of the study that could have caused us to find this when it doesn't really exist. Again, not knowing the truth, what other potential sources of variation could result in seeing a higher rate of lung cancer in coffee drinkers? Well, one of the biggest problems is this thing I've talked about already, which is the observational nature of the study and the fact that people who are coffee drinkers might have other behaviors in common that could actually be increasing their risk. And the coffee may have nothing to do with it. That relationship where you actually have another exposure that is both associated with the outcome of interest and associated with the behavior of the exposure of interest is called confounding. And a known confounder here is smoking. Does anybody have a grandfather who sat around at the coffee shop every morning and smoked cigarettes and drank coffee with his buddies? I did. So I know that that is a relationship that people who self-select into one, not all of them are going to be smokers, but a lot of them are. So you might see more smoking in people who are also drinking coffee than in people who are not drinking coffee. The problem with this is our research question is looking at this relationship, coffee drinking and its relationship or impact on lung cancer risk. So that's where we're really focused. However, if we didn't record other potential sources of lung cancer risk, variation in lung cancer risk, we're probably going to draw an incorrect conclusion, or at least our chances of drawing an incorrect conclusion are higher. The problem is we know that cigarette smoking has a causal association with lung cancer. It's known. So if we were doing this study, knowing that, we should have recorded that, right? And that would allow us to at least tease out the effects of cigarette smoking from coffee drinking. What's also known is that there's a non-causal association. These two are just related habits. They're self-selecting into one and also self-selecting into the other. And it's kind of correlated, a correlated problem here. And so again, if we don't find a way in our design to address this research question of accounting for the variability in lung cancer risk that's associated with smoking behaviors, we're going to increase our chances of finding something that's not really there. And that is the problem of confounding. So confounding variables are any variables that are associated with both the exposure of interest, in this case coffee drinking, and the outcome of interest, in this case is a diagnosis of lung cancer. The importance of confounding is that if we know that it's a problem, we can either, again, design our study around it, record it, and account for it. But if we don't know something is confounding, that's called a lurking variable, and that's the problematic part of observational studies. What we do in observational studies is we try to account for all potential confounders, all potential known confounders in how we sample and how we record data to try to minimize their impact. But there's always unknown confounders, and those are called lurking variables. And true experiments give us some protections against those unknown confounders. Things like randomization will help provide some protection against both known and unknown confounders. Things like blinding and control groups. Without those protections, observational studies are actually at a higher risk of bias for that primary reason right there. So let's take a look at how this played out in our two groups. Let's, again, hypothetically, we know that smokers and non-smokers tend to also be exposed to coffee in different ways because of that related habits, kind of non-causal association. So what could have happened here is that we have our non-coffee drinkers and our coffee drinkers who also happen to be predominantly non-smokers and smokers, and that is actually the cause of the difference in rates of lung cancer diagnosis. Or maybe not. Actually, the problem with this study is not that smoking is causing this higher rate of lung cancer in coffee drinkers. The problem with this study is that it's set up in a way that we cannot figure out with the data whether the difference is attributed to smoking or is it attributed to drinking coffee. There's no way to tease out those effects. So this study is actually very flawed in that it's a waste. It's a waste of resources. It's a waste of time. It's a waste of these subjects' time, of your time, of whatever money you spent on it. Because the way it was designed, even if we had recorded smoking, we would not necessarily be able to separate the effects of coffee from the effects of smoking in order to figure out which of those particular exposures is driving lung cancer diagnosis. And the reason is because of this pattern, where you get the vast majority of smokers also being coffee drinkers, the vast majority of non-smokers also being unexposed to coffee. So it's impossible to attribute variation to one source or the other. So what is this result? It's likely a false positive finding, but again, we don't really know if that's the case. A false positive finding, by the way, some more terminology, is what we refer to as a type 1 error. It's finding an association when an association doesn't really exist. We never know if we're making a type 1 error when we make it. We just know from the design of our study whether or not our chances of making it are high or if they're controlled. So in this case, we had a really high risk of finding a false positive association because we didn't try to account for smoking in looking at that relationship. The result here with this setup, the reason why we have the type 1 error or the increased type 1 error rate is because we have bias. We have a bias in our look at the relationship between coffee and lung cancer. And that bias is actually, in this case, systematic movements away from the truth caused by smoking behaviors. Another possibility that could have happened if we didn't have that really nice, strongly associated relationship between our two exposures here is we could actually end up with another variable, smoking, that is related to or causes variability among individuals in terms of their lung cancer risk that is kind of mixed between our two groups. So this is different. This is a different scenario. Before, we had truly confounded effects of smoking and coffee drinking. Now we don't have confounding. What we have now is actually increased variability in our outcome because we now have two potential sources of variation, and we didn't do a good job of controlling or minimizing the impact of this nuisance variable, which is smoking behaviors. So if you think about it, individuals who are coffee drinkers, if we're interested in what their lung cancer rates look like, we want them to be similar in terms of other potential sources of either increasing or decreasing risk of lung cancer in order to get a really good, clean look at the true relationship between drinking coffee and lung cancer. So this has to do kind of like the signal to noise ratio. This study would have a lot of noise in it because of other uncontrolled sources of variation in lung cancer rates. We'll talk a little bit about how we can change that. So the problem here is, again, the same problem where we do have a potential confounder, but now that confounder is not quite as associated with the behavior of interest. What we can do in this case, which is really nice, unlike the previous case, we can split up and actually partition the variation in lung cancer risk between the two exposures because we have individuals who are coffee drinkers who are now both smokers and non-smokers. So we can actually drill down and figure out which of the groups, the subgroups here, actually have increased risk. So we can do a comparison. It's not quite here. What we'll do, sorry, my arrow is the same color, so you can't see. We can compare the non-smokers who are both coffee drinkers and non-coffee drinkers to see is there a difference there. We can compare the smokers in the coffee drinkers and non-coffee drinkers. So do you see now how we can partition the variability in their risk, in the overall risk among these groups? We couldn't do that before because we didn't have enough smokers and non-smokers of each of these two groups to partition it out this way. So the nice thing about this study is if we have that mixture of exposures between the two groups, we can actually separate out the effects of the exposure of interest from the effects of nuisance variation, in this case, smoking. The problem with studies like this is that when you add or have additional sources of variation, you actually are increasing the noise in your outcome, and it makes it harder to detect a signal. So in statistics, that term is power. The power of a study is its ability to find the thing that it's looking for. And here we might actually miss an association between coffee drinking and lung cancer because we have too much noise in the data, that noise coming from smoking. So that's a problem that we didn't have. I mean, we didn't have it before. We had a similar problem, but a problem in a different way. So again, partitioning it out. One of the problems that ends up happening in this situation that's actually more likely than what I showed you before, where we actually found a difference in the rates of lung cancer, is that you end up missing it. So let's suppose that there is an association between coffee drinking and lung cancer. If there is, and we have this additional source of variation, we might end up with a false negative finding. That is, not being able to detect differences in lung cancer diagnosis rates between the two groups because we have too much noise in our data. That's called a false negative finding, which is a type 2 error. So type 1 is false positive, type 2 is false negative. Something is really there, but we can't see it because we didn't do a good enough job in the design process to minimize other potential sources of variation in our outcome of interest. And this issue, before it was bias that caused a potential type 1 error, here it's just error that causes a type 2 error. It's variation. Unexplained variation or variation that's explained can actually result in a type 2 error. Too much noise in the outcome. So both of those studies can be fixed, right? We don't want to fix them after the fact and have to redo them. So we need to think about these things in advance. So always, always, always give careful thought to your study design. Take time. Don't try to rush from research question to data analysis just to get that publication out there. Really take time, because what could end up happening is if you rush through, you could end up with a study that's meaningless. Either you have too much noise, so you're underpowered, and you miss a finding that, oh, I knew it was there, but look, I just didn't have enough data because it's too noisy. Or you could find something that doesn't exist. And then when you submit it, one of your peer experts who's reviewing will say, well, what about this other variable that you didn't consider? And then the study ends up not being publishable, and unfortunately was a waste of resources in the first place, which can be an ethical problem, right? It's a scientific ethics problem. So the different ways that we could control for issues like this in the design of a study is collect information on all known alternative sources of risk. So what else increases risk of lung cancer that we could actually record pretty accurately in these individuals? That's one way of helping. You can also limit your sampling based on those known alternative exposures that increase risk. So we can have only looked at non-smokers. The second bullet point actually helps us with our power, right? It does impact our generalizability. In other words, how broad our conclusions will apply. It will only apply to people who don't smoke. But at least we'll be able to get adequate power with our finite resources, as opposed to trying to do a much broader study that is more generalizable, but is really expensive and time consuming to do. So again, there's always a weighting process between feasibility and a perfect world where we could answer the question exactly how we want to answer it. So again, back to what statistics does. You've seen here some aspects of really all we're doing in all statistical methods. We're just trying to figure out where's the variability in an outcome coming from. And we do that first by designing a study in a certain way so we can isolate the effect of an exposure or a treatment and actually detect it with a powerful study. And then what we want to have is a valid, reliable estimate of an association or a difference. And we want to be able to replicate that, right? We want to do it in a rigorous way so that hopefully the result can be replicated in another study. So statistics as a science allows you to manage uncertainty, manage variability, and also quantify it. So we manage it through the design of the study and how we collect the data. We quantify it when we analyze the data, and that's what we're going to focus on in the remaining 3 weeks in the context of the different study designs that we're going to see today. Quantification of uncertainty comes in many ways, and it's probably terminology that you've at least heard if you're reading the literature, if you're doing your own research. Quantifying uncertainty has to do with those error rates, type 1 and type 2 error rates. When we design a study, we actually look at relationships between sample size, the actual overall design, the type of outcome that you're collecting, what associations you're looking at, and try to minimize the risk of making a false positive or false negative finding through the study design. We also try to increase the power of a study, increase its chances of finding a meaningful difference or a meaningful association if it actually exists. We also quantify uncertainty through p-values. P-values are really interesting. They're just probabilities, but probabilities of what? We'll talk about that, not today, we'll talk about it next time. So we understand what p-values are, but more importantly, what they aren't. Also, when you should apply them and when you shouldn't. Has everyone heard the term standard error? Often in a table you'll see results reported with like a mean and a standard error. The standard error is a quantification of variability. It's a quantification, if you will, of sampling variability. So it allows the reader of your manuscript to say whether or not your estimate of the average outcome in these patients is reliable. Is it precise? Or is it the standard error too large and the result itself doesn't have a lot of weight behind it because you didn't have a lot of precision in your estimation? Confidence intervals quantify uncertainty. Confidence intervals are generally preferred over p-values actually because they give you not only the significance of any result that you find, you can actually tie it back to how statistically significant is this result. But it gives you the clinical significance, because you get an actual estimate of what effect you're looking at. Is it rather large? Is it small? Is it precise or imprecise? So confidence intervals contain all the information that you really need for interpreting the results of a study. And then, of course, proper interpretation. Statisticians are trained to think about context. So you can apply a t-test or a linear regression model to any type of data that's generated from any type of study. And the results quantitatively will have the same meaning. But if we think about the strength of the results, that is tied directly back to all the limitations of the study design. So proper interpretation in light of the context that produced the data, that's another thing that statistics provides through the experimental design process. So I'm going to pause there. Any questions about statistics in general, or any of the terminology that I've covered? Yes.
So in observational study, you will have to know what are the other risk factors associated with the outcome. So if it is unknown,
Yes. So the question was, in an observational study, you're limited to what you know. So you can only control what you know in an observational study. If I know smoking is a risk factor for my outcome, I'm going to figure out how to incorporate it into my design to minimize its impact on my look at coffee drinking and lung cancer. But let's say, there are other things that can increase your risk of lung cancer that we don't know about yet. So how would we control for that in an observational study? There's no way, right? If we know about it, we can at least record it or try to control for it in our sampling or stratification or in a regression model. That's the benefit of an experiment. An experiment, and I hate to use the term experiment because it has a negative connotation when we're talking about humans, but that's what a randomized controlled trial is. It is a rigorous method for testing for differences or for associations that applies experimental principles. So if we let's think about radon. Everyone knows what radon is, radon gas. It's really actually a problem in Kansas. If you have your house built in Kansas and you have your basement, it's potential that you're actually getting this colorless and odorless gas seeping into your basement that can increase your chances of lung cancer. You can smoke or not smoke, and it could cause you to have lung cancer. Let's pretend we don't even know it exists, right? But it's a very strong predictor of lung cancer. Not knowing that exists in an observational study, it could cause a lot of problems, either with increased error in the outcome, increased variability in the outcome, or bias, depending on what the relationship is. So it's going to cause a lot of problems, and we don't even know it exists. If we were doing a randomized controlled trial, even if we don't know it exists, randomization helps protect against that, right? Because the idea behind randomization is that if I have 50 patients or 50 people who I'm going to put on my study, I'm going to randomly assign them to be exposed or unexposed to whatever it is. If it's coffee drinking, that doesn't make sense, right? Randomly assign them to a treatment or a control. And so the randomization should theoretically balance out all unknown confounding variables. So we should get about half of the radon cases in one group and about half in the other through randomization. So that's why randomization is a protection that observational studies don't have, and it's why it's preferred, because it protects us against unknown confounding variables. Looks like somebody shared screen. Okay. Does that kind of make sense? So that's why observational studies have such a high risk of bias, because there are so many things that are unknown that could have caused the association that you see. Whereas randomization minimizes that risk and allows us to kind of have more confidence in the conclusions of the study. So that was a great question. Let's move on to evidence-based medicine. Evidence-based medicine is really just making decisions, practicing, using the most updated level of evidence in the field. The nice thing about evidence-based practice in anything is that it increases the chances of making correct decisions, of implementing correct policies, of administering the best treatment, of improving or getting the best patient outcome, because you're using the best and most updated evidence. There's a process behind this, though, and the process is that we have to actually gather the evidence first, right, and then disseminate it. The important part of dissemination is that we have to, as researchers, make sure that we are not trying to overstate our conclusions. We have to make sure that we understand the data from our experiment has limitations, and we have to put those limitations out there. We have to be very clear about what we did and did not find, And what we found, you have to be clear about the risk of it being real or not. And the whole process underlying this is the scientific method. So when I talk about types of evidence, scientific evidence actually has different levels of strength. Not all data is created equal. I think that's pretty obvious, but what we want to try to do today is tie the quality of data back to the context, the type of study that generated it. So for instance, the highest level of scientific evidence is going to come from a randomized controlled trial or some kind of systematic review of randomized controlled trials, because those apply principles of experiments to looking at associations, to identifying and estimating associations. Systematic reviews of randomized controlled trials are actually at the very top of the hierarchy, because systematic reviews of clinical trials synthesize all of the scientific evidence from multiple primary RCTs to try to figure out what the quote-unquote truth is, right? We never know the truth, but to get the best guess at what the truth is. So it's always better, one RCT is great, 5 is better, right? As we move down the strength of evidence, obviously, not all randomized controlled trials are created equal, which is why it's always important that when we write up the results of a study that we did, we are so clear in our methods that someone who wants to replicate it could turn around and replicate it without ever having to talk to us. You need to write down your methods and procedures like a protocol and submit that maybe as an addendum or some kind of online supplement, so people will know, even if you don't clearly state all limitations, they can go to your protocol, for instance, and see, oh, well, they didn't do it this way, so maybe that's why this study is different from that study, even though they're two primary studies designed to detect the same thing. So some RCTs are lesser quality, they're not as big, they're not as rigorous. Some observational studies, like cohort studies, and in particular prospective cohort studies, will be kind of moderate quality evidence, or systematic reviews of any of these will provide some moderate evidence. Moving further down, as I'm moving down, what I'm doing is I'm losing different experimental principles from the study design. I'm removing randomization, for instance. I'm removing prospective observation. I'm removing blinding. I'm removing a control group. I'm removing other aspects of experimentation. And so anytime I remove one of those things, I actually weaken my evidence. So I can go all the way down: retrospective cohorts, case control studies, case series, which is just looking at a series of interesting subjects, interesting cases, and maybe how their treatment worked or did not work. And then finally, at the very bottom is expert opinion, case report, clinical example, or evidence based on physiology, bench research, or first principles. I want to be clear here: just because something is at the bottom of this table does not mean it doesn't have value. In fact, every scientific endeavor, unless you got really lucky, probably started at the bottom and worked its way up over time, right? Science works in baby steps. Usually we start off at the very bottom by accident. We find something by accident, and then we move forward and forward and forward, and finally, multiple really high quality randomized controlled trials can confirm what we found at the very bottom here. So I don't ever want anyone to think, if you're doing something that's at the bottom, that it doesn't have value. When it doesn't have value is if you're staying at the bottom and doing the same thing over and over and over again and not pushing it forward through the pipeline, correcting and moving forward. That is the scientific method, right? We find something by accident, we observe it, literally by accident usually, and then that allows us to formulate some kind of hypothesis and figure out, well, what's feasible here? Can I get some preliminary evidence for this? So I look at, maybe it's a case study. that informs a hypothesis. And from that, maybe I go out and I look in electronic medical record data for other patients who had similar problems or treatments, and try to do maybe a cross-sectional study, which is a very inexpensive way of trying to get more evidence for the same thing that maybe I found in a case study or a couple of interesting cases, like a case series. And then I either find something that confirms my original hunch, my original hypothesis, or maybe I need to revise a bit and do another cross-sectional study. The point is, this is a cyclical process that eventually, hopefully, leads to closer and closer to the truth. It can kind of come off the rails sometimes, unfortunately, because of the problems with the strength of evidence at the bottom, right? We're not always going to have a fruitful path every time. In fact, I would say probably the vast majority of times end up stopping before they get all the way to the top. But the point is, the scientific endeavor moves forward. But applying evidence-based practice in medicine, and really in any field, means that the practices that are being applied are those that have been rigorously investigated and found to be superior in some way to other known alternatives. And implementing evidence-based practice actually increases the chances of successful patient outcomes, and also sets up a system where we're making more efficient use of healthcare resources. The way that this looks in clinical evaluation, it's a perfect mimic of the scientific method. We start, again, with observation. Bless you. That observation can be very simple. In the clinic, we see a case. In the lab, we see a really weird result in an experiment that we did the wrong way on accident. But that's data, some kind of evidence or information. It allows us to create a research question and then design some kind of study around that research question to see whether or not the study confirms that hypothesis or refutes it. From the new data, then we go back through the cyclical process, and hopefully at some point we move from bench, from the lab, to patients, from patients into real clinical studies, simple and then large RCTs, and then maybe eventually we have a breakthrough in treatment for patients. But the idea is that we don't always need to establish causality or establish relationships. We might only need to be exploring or describing or classifying individuals. So we have to be careful about understanding not only the limitations of what's in front of us in terms of what money we have, what resources we have, what patient populations we're dealing with, but also where is the current state of knowledge? Do I need to be doing a phase 2 randomized controlled trial? Or should I be doing something smaller? Should I be doing a phase 2 if there have been a lot of other phase 2 that have been done? Should I try to find a way, either through some kind of collaboration, to do something larger, more confirmatory? So understanding where the current state of knowledge is will tell you what you should be trying to do with your research question. The type of study then would be determined by what the purpose of your research is. Should you be doing a descriptive study, an observational study, or should you be doing some kind of experiment, true experiment, like a randomized controlled trial? Obviously, you exert more control over the situation the further down you go, because you're decreasing the ambiguity in your results. You're actually getting stronger evidence using the scientific method. So back to experimental design, what we're going to talk about for the remainder of the hour are the ways in which we can address a research question using study design. Not all studies are experiments, but the gold standard is. So experimental design, again, is a set of techniques for planning and conducting studies, emphasis on planning, because planning takes time. It does take time to understand what needs to be incorporated in the design to increase our chances of making a correct conclusion. All of the different things that fall under this paradigm include Formulation of the research questions. We have to really know what we're after in order to make it into a testable hypothesis. We have to also determine the conditions of the experiment, the standardized procedures, the measurements that we're going to collect, and any other extraneous conditions that we want to control for in the design. So those extraneous conditions are kind of like smoking, right? Smoking is that additional source of variation. It actually increases risk. So we either want to collect it, or maybe we actually want to control for it in some way. We want to stratify how we randomize patients, or we want to limit our patient population to those without that extra exposure. We also have to do the appropriate sample size calculation for the study. So that sample size estimate is what most people think of when they think of experimental design. They think, really all we need to know is how big the study needs to be. But it's all of these things combined for the overall study design. So the sample size is directly related to what your hypothesis is, what your experimental conditions are, what measurements you're actually going to use, what conditions you're controlling for, what statistical analysis you're going to perform. I have to know, as a statistician, all of these things, plus how you're going to assign your subjects to the different experimental conditions, treatment or control, treatment 1, treatment 2, control, that kind of thing. Before I can even get an estimate of the sample size required. The sample size estimate, by the way, takes into account all these features, and then it gives us the sample size required to minimize your chances of both making a false positive finding and a false negative finding. That's where that sample size estimate comes from. And it is truly an estimate. You might find at the end of your study that we didn't do a good job of understanding or predicting what the data was going to be like, and we end up with a sample size that's not adequate. It might have been too big or too small at the end of the study, which happens, right? It just depends on how well we are at predicting some of these extraneous conditions and other sources of variation in our outcome. But the ultimate goal of designing an experiment is to increase our chances of drawing correct conclusions. And the way we do that is we minimize bias, minimize sources of bias, minimize their impact on the look at the relationship between exposure and outcome. And we also minimize error. Error is just any unexplained variability in the outcome that might mask any true signal. So the ways that we do that in experimental design, we apply randomization. We try to apply random sampling, where we're actually randomly sampling individuals from some patient population to include on the study. We incorporate control groups, positive controls, negative controls, null controls, to allow us to tease out some other potential sources of bias that could result in finding something that's not actually there. We apply blinding, because people are people, right? If I feel really strongly that this treatment works, and I know that patient got that treatment and that patient didn't, what am I going to do if I'm evaluating the response? I'm going to bias it, even if I don't want to. So it's just better to remove the knowledge, so the pressure's off, right? We even blind statisticians. Statisticians know that the investigator really wants to find that meaningful difference because they feel very strongly that their treatment is good and it works. And so statisticians prefer to be blinded. We have treatment A and treatment B, but we don't know what A and B are, and that removes the pressure from us. We just do the data analysis according to the statistical analysis plan, write it up. It removes our knowledge of what the result actually means. So then we are able to write things up with a critical eye without any of the bias for maybe overstating or understating conclusions. Because we didn't find what we wanted, we understated. We found what we wanted, we overstated. You know what I mean? So blinding is very helpful for everyone. And finally, the perspective observation. So being able to observe something happening in front of you, as opposed to relying on subject recollection or relying on electronic medical records, all of which are flawed and can result in misclassification or in measurement error. So the more of the protections that we put in place, the stronger the level of evidence produced by the study, which is why you see randomized controlled trials at the very top of the hierarchy. So here are the studies that I'm going to cover today along the right-hand side. Notice that they increase in complexity and confidence as you move down. This is a pretty standard hierarchy of study designs. You see a combination of what are called descriptive and analytic studies. Descriptive studies are really designed to just tell people what you saw. I'm going to describe what I saw. I'm not going to test hypotheses. I might generate hypotheses that can then be tested in analytic studies, but the purpose of case reports, which is, again is a very thorough and rigorous description of a very interesting case, or a case series, which is the same thing only applied to more than one case, or a cross-sectional study. A cross-sectional study is a snapshot in time. There's no temporal, no timing sequence between an exposure and outcome. Those happen on populations and individuals, and the purpose of those are really to generate hypotheses, not to confirm anything. Don't do hypothesis testing, for instance, in those. Analytic studies, which can be then classified into observational and experimental. These are comparative studies. I'm going to compare groups, but I might do it with a lot of potential limitations, like in an observational sense, or I might do it in a truly experimental situation, like a randomized controlled trial. You often see this in the pyramid form, where we have the hierarchy of scientific evidence. You can see randomized controlled trials are right here, technically at the top of the pyramid for individual studies, because above that are two approaches that are actually kind of the same thing for synthesizing the results of many randomized controlled trials that might actually have conflicting evidence to try to get at a better, more focused view of what the association actually is. We'll talk about those at the end of this 4 weeks. But we're really going to focus on individual studies. Randomized controlled trial is the gold standard. As we move down the hierarchy, we're actually removing some aspect of experimentation. When we go from a randomized controlled trial to a cohort study, we remove randomization. That's basically it. A cohort study is a non-randomized trial. When we go from cohort to case control, we could be moving from prospective observation to retrospective observation. Forward inquiry, backward inquiry. So again, all we're doing is we're kind of increasing the risk of bias as we move down by removing some protections. And finally, cross-sectional and ecological, again, actually removes the component or the aspect of time altogether, because we don't know whether the exposure immediately preceded the outcome, if it preceded the outcome a long time ago, or if it even preceded the outcome at all. It could have actually happened after the outcome of interest. We just don't have a way of verifying that. So let's start with the gold standard so we can see how we peel back each of these individual parts. So the randomized controlled trial is the only true experimental study that we perform in humans. The defining features of the randomized controlled trial, obviously, investigators are exerting control over how patients are assigned to treatments, preferably through randomization. Otherwise, it wouldn't be randomized controlled trial. There are other ways of assigning treatment or assigning exposure, but randomization is the preferred method for what I just mentioned a few moments ago, which has to do with trying to balance out unknown factors that could influence or bias the look at the exposure outcome relationship. Another key feature of this is that they're prospective. We observe both the treatment or the exposure and the outcome. We observe them in front of us, so there's less chance of misclassifying it, if you will, than if we did it retrospective, which would be relying on historical recollection, either through EMR or subjects' own recall. Another aspect of this, by definition, since it's perspective, is we have a forward direction of inquiry. This is really not important for an RCT in terms of a defining feature, but it will be when we get to case control and cohort study. What we mean by direction of inquiry is when the exposure occurred relative to the outcome and which of those we use to define the population. For instance, if I'm doing forward directional studies, I identify my patient population and then the exposure happens first. Treatment or control, exposed or unexposed. And then I look forward in time, either prospectively or retrospectively, to see whether or not the outcome happened. Backward directional means that I actually start at the back end. I start with their outcome, and then I look backward to see what their exposure was. So there's a better picture here, I think, that's helpful of what we mean by retrospective. So this is retrospective versus prospective. In the middle, we have present day. This is happening right now. Randomized controlled trials and prospective cohort studies start today, and we follow them into the future. We observe everything in real time. Retrospective cohort studies, case control studies, occur prior to today. Everything already happened. I have to go find the information. Either I have to ask the patient, I have to dig through EMR, or something else, right? Everything's already happened. Cross-sectional, present really isn't the right term. Just know that it happened at a single point in time. There is no temporal component. When we move into the past, we have a high potential for bias. And that should also include our cross-sectional study, because it's just, it's relying on retrospective information that occurred at a single point in time. So there's no temporal component. Another defining feature of randomized controlled trials is the idea of a control group, but not just any control group, a concurrent control group. That means that what's happening is I'm randomly assigning subjects to either exposure or no exposure, treatment or control, and I am treating them the exact same way. I'm observing them the exact same way, all the way to the end of the study, with respect to everything except what? The treatment of interest, whatever it is I'm testing. So the control group might be getting a placebo that looks and smells and tastes the same. It's administered in the same way. I'm following them at the exact same follow-ups for adverse events. I'm giving them the same attention that I'm giving the treatment group. The only way the treatment group differs, theoretically, is that they have an active ingredient in their pill that the placebo group is not. They're getting the exact same treatment otherwise. And so when we have that assurance, including randomization that balances out all other unknown potential sources of variation across the two groups, then at the end of the study, if I see a difference, I feel really confident that difference is because of that active ingredient, not because I followed up with the treatment group more frequently, or relied on a control group that was treated in the past and had other things that could have been different than what I'm working with in my treatment group. Randomization, I don't think that there's any lurking factors that could cause the result. And finally, the randomized controlled trial is the only study that can be designed to attest to a causal relationship between exposure and outcome. So this is a picture of a randomized controlled trial. We just notice this is the theme series for the remainder of the study designs. Along the bottom, we'll have time. The star will be kind of where you are currently, where the study starts. So a randomized controlled trial begins by defining the population. That's the star. Then we randomize, we exert control over the treatment assignment. I'm just going to say treatment and control, or exposed, unexposed. We follow them forward in time to record whether or not they have, let's say, a positive outcome to treatment or a not positive outcome. I'm not sure what the situation here is. The two things, prospective observation means I'm seeing things happen in real time. Forward direction of inquiry means I see first exposure, and then I move forward and see outcome. The key to a randomized controlled trial is what I just mentioned, that the groups of patients that I'm comparing, because of randomization, because of the prospective nature of the study, because of the standardized processes and procedures I have in place, the groups of patients I'm comparing are similar in all respects, with the exception of their exposure. Some are treated, some are controlled. So at the end of the study, if I see a difference, what do I attribute that difference to?
Exposure.
The difference, right? The only difference that should be here, which is the exposure. There's always a chance that it could be due to something else. But again, that's the idea behind minimizing the risk of a type 1 error. We never know if we make it. We just know that our risk for making it is really small. So when we find something, we say, of course, it's always possible, but it's less than 5% chance or less than a 1% chance that this is a false positive finding. That's our level of significance. So the strength is controlled assignment of exposure, uniform application of exposure and observation. They establish both a temporal relationship between exposure and outcome, and potentially, depending on how they're designed, could establish some kind of causal relationship. They have prospective observation. Their weaknesses, they can't always be done, either because they're not feasible, they may take too much time, they may take too many resources, they might not be ethical, because you can't randomize, for instance, people to smoke or not to smoke, right? So that by default, if I was interested in the effect of smoking on lung cancer, I couldn't do that as a randomized controlled trial for ethical reasons. Another problem with any prospective trial, where we're following them in real time and we're following them longitudinally, right? Let's say we follow them 6 months, 12 months, 10 years. One thing that happens is attrition, right? So you had a patient at baseline, agree to do it, you gave them treatment, you recorded some information, and they needed to come back in 6 weeks, or they needed to come back in 4 weeks, or maybe you need to be able to follow up with them in a year. Sometimes you can't get in touch with them. They don't come back for appointments. They pass away, they move, whatever. So that is a real weakness of any prospective study, not just randomized controlled trials. And a primary reasons. The primary weaknesses here are feasibility because of cost and time, and then loss of follow-up. So if those are limitations that cannot be overcome, then you can do an observational study. One step down is the observational cohort study. It's just like a randomized controlled trial in some cases without randomization. You're just observing people self-select into their exposure status. Either they decide to take some kind of medication, a certain type of medication for their cholesterol. They chose to do that. Or their doctor recommended them do that based on some kind of clinical decision making, rather than randomly assigning them to take that medicine or not. This is still forward directional, so I see first the exposure, move forward to collect information on the outcome. It's also designed to assess associations between exposure and an outcome that's subsequent to exposure. But cohort studies can actually occur in 2 ways. They can occur prospectively, which is that nice real-time observation, which minimizes the problems with that come along with historical recollection of information. But they can also occur retrospectively. Everything could have already occurred in the past. We tend to do retrospective cohort studies if they're the most feasible. If the data already exists, we can just go back and collect it. So you'll usually see that defining feature. And why do we need to know whether it's prospective or retrospective? Because as we critique the literature, we need to understand the context that produced that evidence. And so if a cohort study is prospective, I know, well, this is probably a little bit better than if it had been retrospective. Because if it's prospective, I know that they saw these things occur, and it's less likely that they misclassify either exposure or outcome. But if it's retrospective, they had to go into EMR, they had to ask subjects for information, and that has other issues with it. Prospective cohort study looks just like a randomized controlled trial. Notice though, we removed randomization. So the key is when we remove randomization, we weaken the level of evidence. We no longer have assurance that these groups of patients are similar in all respects, with the exception of the treatment, because there could be lurking factors. There could be unknown confounders that could cause an association when association does not exist. There could also be unknown factors that are increasing the error in our data that would make us miss an association. A retrospective cohort study, notice all I changed was where we are in time. So retrospective just means it's the same study design, it's just all the data, you have to go back and collect it. Forward direction of inquiry, notice, is defined by the fact that I'm actually selecting people for my study based on their observed exposure. And then I'm looking past that to find their outcome. That's what forward direction of inquiry means. We'll see in a moment what case control will clarify that concept, because we're actually going to have the backward directional study. So the strengths of an observational cohort study, again, I mentioned we would prefer a randomized controlled trial, but a cohort study might be necessary, for instance, if randomization isn't ethical or feasible. So they do still establish that temporal relationship between exposure and outcome. They're also really useful and efficient for rare treatments or rare exposures. If there's only 20 people in the world that ever got this experimental treatment, I might want to try to get all of them for my treatment group and try to find a very similar control group of patients and then follow them forward in time and do a comparison. If they're retrospective, so if I have a retrospective cohort study, that's even more efficient than a prospective study because everything's already collected, right? Everything's already out there. The data exists. That's a really good study design when the time between an exposure and outcome is long. That's often when retrospective studies are applied, right? So if I know that an exposure happens and I have to wait 20 years before I'm going to start to see outcomes, then I don't want to do that prospectively. I don't want to be waiting around for 20 years before I know how my study's going to end. So I want to maybe define that study using retrospective data. The weaknesses of observational cohort studies, obviously, there's a lot of potential for bias. If they're retrospective, you have the additional problem with misclassifying either the exposure or the outcome from that historical record. If they're prospective, you have kind of the same weaknesses that a randomized controlled trial has. Loss to follow-up, and they're very resource intensive. One step down is the case control study. So cohort study looked like a randomized controlled trial minus the randomization, the prospective cohort study did. A case control study, its defining feature is the backward directional aspect of this. So if we take a look at what this means, it's by definition retrospective, but it's also no longer forward directional. Case control, its name actually describes its defining feature. You have to define your population based on some interesting, some targeted outcome or disease. Lung cancer. Let's go back to our lung cancer example. So I'm really interested in looking at lung cancer patients and figuring out what happened to them or what did they do or what is their genetic predisposition. I'm going to look back in time and see what potential exposures could have led to their lung cancer diagnosis. I can't do that with just a group of cases because I don't know then if people with lung cancer have the same exposures as people without lung cancer, right? So that's the only way I know whether or not those exposures are associated with lung cancer or if everyone just has them at the same rate. So I have to have a control group. So that's where we get case control. So I define my cases. I have a very carefully selected group of controls. Usually I try to match them in a way that mimics randomization. So if I have a 50-year-old African-American man, then I try to find another 50-year-old African-American man without whatever condition it is. So if he's got lung cancer, I try to find a very similar in terms of any other risk factors for the disease, but without the disease. And so what that does is it kind of mimics randomization in a way, but not perfectly. And so the backward direction of inquiry means once I have my cases and controls defined, then I can go back and look at their exposures, look at their past behaviors that could have influenced the development of their disease. Everything, again, is retrospective. So you can see, not only do we no longer have the assurance that the groups being compared are similar with all respects, in all respects, but we also have the problem of historical recollection in this case. But case control studies are very useful. They're actually very useful when you have rare diseases, right? So if I'm defining my cases based on their disease status, if there's a disease that's happening, or maybe a rare outbreak, an outbreak of a particular illness, then I can grab those individuals and then figure out, well, how are they different from a very similar group of controls? Cancer clusters could be done this way, for instance, to find a very similar population and try to tease out what the differences are. They still establish that timing between exposure and outcome, only now we're identifying their outcome first, defining our population based on their outcome and then looking back in time. The nice thing about these also has to do with the fact that I don't have to just focus on a single exposure, right? I can look at many different possible exposures. So anything that's a candidate for increasing risk of this particular disease could be collected if the information is there. The weaknesses have to do with all the weaknesses that come along with removing randomization, removing a concurrent control, right? Meaning it's being observed and treated and outcome measured at the same time as the treatment group. The way that we select cases and the way we select controls, there are actually, you can increase the risk of bias if you're not selecting your controls from the same theoretical population as your cases, right? That could actually change or bias to look at the relationship between exposure and outcome. And again, of course, they're dependent upon subject recollection or historical records. There's a lot of potential for misclassification there. One step down from a case control study, peeling away again layer by layer, cross-sectional studies are non-directional. It turns out that you might have access to a wealth of data, but no timing information, right? So you know people have an exposure, you know how they have an outcome, but you don't really know when either of those occurred. You don't know for sure if one occurred before the other. So cross-sectional studies are non-directional. They allow you to look at associations between exposure and outcome, but not to really state that one precedes the other. That's a limitation of that. And again, it's historical, so it relies on historical record. Notice it looks like the other, like a cohort study or a randomized controlled trial, but there's no time. Time has been removed here. Everything occurs not simultaneously, it's just that we don't know necessarily the particular timing of exposure and outcome. The strengths of cross-sectional studies, these are facts. I mean, if you have data, you can look for associations in a lot of things, right? To generate hypotheses that you might then go and try to find data for a case control study or a cohort study to then establish the temporal sequence between exposure and outcome. You can also study many different exposures and many different diseases simultaneously. It's kind of like data mining data, right? The weaknesses of cross-sectional studies is just a weak level of evidence. You're not establishing anything, you're just gathering preliminary information. You can't, you also can't identify incident cases. So you don't know if it's the first time someone's been diagnosed with something if you don't know when that diagnosis occurred. So incidents can't be estimated. You can't estimate risk with cross-sectional studies. Another problem with cross-sectional studies is that you can actually miss acute conditions, which means that something happens and it resolves really quickly, or it happens and the individual dies very quickly. So if you're just looking at a snapshot in time, you might actually miss those. The last study, which is very popular, it's a population-based study, more EPI. type of study is an ecological study. And this is a descriptive study, just like a case control or a cohort study. Its purpose is really descriptive. The difference is, rather than having an individual patient's information, you have information summarized at an aggregate level. So maybe you have it at a state level. So I know the percentage of individuals in the state with this particular condition, rather than each individual person in that state, what their actual status is. So it's all aggregate data for both exposure and outcome. And so you can really only examine associations at a group level. You can look at it by county, by zip code, by state, by country, maybe even, I'm saying it in terms of geography, but it could also be, sex-based or race or ethnicity-based, any classifier that you may only have information at the group level. So that's a definite alternative, especially whenever other types of studies aren't feasible. And it might also give you a really quick look at an association that you might then try to invest resources for more specific subject level data. Here's just a quick example of looking at something by state for firearm legislation and firearm related fatalities in the United States. This is a public health problem, and trying to take a look at what's the relationship between the strength of legislation, the amount of legislation restricting firearm use, firearm ownership, and the rate of firearm fatalities in the state. So you might see a decreasing association here, but you can't see it necessarily at the individual level, right? So there might be other features about these populations that would cause an association to appear and then to disappear when you look at it at an individual level. For instance, this is a great picture of how that can change. That association can change when I look at it at an aggregate level on the left and an individual level on the right. So on the left, it looks like I have some exposure on the x-axis, some outcome on the y-axis. So increasing exposure results in increasing outcome. But when I break it down to individual people in those 4 different countries, there's actually a decreasing relationship between exposure and outcome. It's just the countries themselves vary in both exposure and outcome. Countries with higher exposure also have higher outcome for whatever reason. So this is a problem. This is called the ecological fallacy, where you have to be very careful. This is another source of bias, if you will, when you're working with aggregate data. Not only can you find something that isn't there, you can actually totally reverse the relationship in an association if you're not careful. So finally, Gary Gronzif gave a talk several years ago when I first started here that focused on subjective or evidence-based practice in medicine, but also acknowledging the subjective components to this. So you can get so far on your training, on principles, and on the evidence, but at some point you have to make the leap using your judgment. So there's some subjective decision making, not just in how do I treat a patient, but also in do I use a case control or a cohort study. 2 investigators who are of equal credentials and equal training, who are both brilliant, might choose to address a research question in 2 different ways. And so you might actually end up with 2 different conclusions because of that subjective level of decision making. So the key is, and I hope to reiterate this for the remainder of the 4 weeks, is that it doesn't matter if we have to make subjective decision making. We just have to be transparent and justify it, right? So that it can stand up to a rigorous evaluation from our peers. So they'll understand that there's the decision making behind any of these processes. And so we also take that into account when we critically evaluate the merit of any study, one that we're doing or one that we're reading in the literature. We have to look at the context. We have to look at the type of study. We have to look at how clear the methods are. And that will allow us to then kind of classify the level of evidence, the weakness the strength or the weakness of the evidence in order to further define our own research path, and also if we're physicians treating patients, determine what the best path for treatment is for patients. And a reiteration of experimental design. Our overall goal in any study is to try to isolate and detect the effects of an exposure on an outcome. It's not always possible to do this perfectly because of the resources that are needed to do a true experiment, and also because of the limitations of time or maybe ethical ramifications of any particular aspect of that experiment. So we work where we can in the realm of the scientific method in terms of the hierarchy of evidence from study designs to try to identify the best balance of feasibility and necessary controls in a study to get at the research question and to move science forward. I want to stop here. We have about 5 minutes left for questions, but I wanted to provide a plug for a tool that I really like. I know people have their preferred data analytic tool or visualization tool, and it might be specific to your field, but our studio is really, really good. If you aren't scared off by just a tiny bit of programming, what I mean by programming is knowing that if I want to do a t-test, I have to write t-test and then tell it something. This offers kind of an integration of point and click and programming. And the programming actually, what do you call it whenever you start to type? It's like Google. Whenever you go to Google something and it autofills, it'll autofill a lot of things. It has fantastic help, fantastic tools for visualization, and it's a platform that's free. And our studio, the company, has created a lot of great webinars. So if you're looking to expand your analytic tools, this is one that I recommend that has a lot of online resources and a lot of online videos, a lot of online help for people who are trying to do data visualization and analysis. Okay, questions? Feel free to ask them now, or you can email them to me. Yes.
I'm going to go back a bit. What's the relevance of a p-value in a clinical research setting?
What is the what of the
The
p-value?
relevance, the significance of a
The
p-value.
significance of the p-value?
Yeah.
It's funny that you use the word significance for p-value. Okay, so the significance of the p-value in a research setting. We are going to talk about that a lot at the beginning of next Friday's. I'm going to define what it is. I'm going to actually show you what a p-value represents. And all a p-value does, it represents sampling variability. That's all it does. So we're dealing with samples. One of the biggest risks that we have when we do research using samples is that we might find things that are simply a function of our sample. Does that make sense? We might have sampled in a way that gave us a result that wouldn't have occurred if I had sampled in the exact same way and just ended up with a different group of patients. So that's the risk of sampling variability. And so the p-value tries to quantify the risk of sampling variability and producing the result that we found. So if I do a study where I'm sampling 10 patients from a population, I'm looking at their average BMI. And someone else does the same study in the same way, samples from the same population, 10 subjects, they're going to get a different estimate of the average BMI. And so what I might be interested in doing is testing in my sample whether my BMI indicates that this population I'm sampling from is overweight or obese. And so my p-value will try to quantify whether or not, so if I found that my sample is overweight or obese, my p-value will say, what is the risk that this is a function of sampling variability? That it's just because my sample, and actually my p-value for a sample of size 10 should reflect that risk is high. It should be a big p-value. So if I have a big p-value, I have big risk of finding something as a function of sampling variability alone, as opposed to it being a real meaningful effect. That's why we like small p-values, because small p-values convey to us that the risk that this is a result of sampling variability alone is very small. The problem with the p-value is that it is directly related to your sample size. And so you might end up with an artificially small p-value just because you have a lot of data, not because you actually have a small risk of this being a result of sampling variability. People don't apply them correctly, not in general, but they're overused and misused. And I think that there are ways to remediate that are very easy. It's not to say that you should never use p-values, but if you use them, you shouldn't rely on them too heavily. Confidence intervals are much more preferred to p-values. They'll convey the exact same information, but they'll actually convey more meaningful information than the p-value will. So if I get a confidence interval, it will tell me a little bit about the risk of sampling variability producing a result. It'll actually tell me the exact same thing that the p-value tells me, but it will also give me an estimate of the actual effect that I found. The p-value won't give me that. The p-value, again, could give me kind of misleading information depending on, if we have to understand when it's appropriate and when it's not. We do have another question. Are there guidelines for deciding when to stratify your sample and when you have stratified too much? There actually are, Sean, and those are related to sample size. So preferably you decide what you're going to stratify by when you're designing your study, so you take into account that stratification and an estimate of how big your study needs to be. Because the more you stratify, the larger your sample will need to be. So it's just a design. You don't want to stratify after the fact if you don't have to, because then you could increase your chance of missing an effect by diluting your sample too much. Stratification factors. And I see Jennifer asked earlier if the slides have been sent out. The slides have not been sent out. If people want a copy of the slides, I can let them know. I know people like copies of slides. I don't like to send them out, though. It's fine. It's because I'm making minor changes all the way up to the minute, usually. Try to refine. So, any other questions? Okay, I have anyone who has parking that needs validated, please see me up here. If not, I will hopefully see you all next Friday, either online or in person. Thank you.
So what if I park in P2